All right, hey AP Chemistry. I wanted to post another video on how we use what we've talked about with writing equations or writing acid dissociation equations and working with equilibrium calculations and buffers. Okay, so let's just do a simple, let's say I have 0.100 molar of HCN, and I'm asking for what's the concentration of H plus at equilibrium, or what's the pH? Okay, so let's say those are my questions. Okay, now if I have HCN in a beaker, it is going to be in equilibrium with its conjugate acid and base. And so since it's at equilibrium and it doesn't fully dissociate, in order to figure out what my concentration of H plus or pH is, I need to use the Ka. So I cannot automatically say that my concentration of H plus is 0.1 because it's a weak acid. If this was a strong acid, if I had 0.1 molar of HCl, which is a strong acid, the concentration of H plus would also equal 0.1 molar, and the pH would be the negative log of 0.100 molar. Okay? But I can't do that with this problem. This is a strong acid, and I'm working with a weak acid here. And there are two ways of identifying something as a weak acid. One, if I give you a Ka, you're making the assumption that it's a weak acid. The Ka automatically tells you, hey, this thing here is not fully dissociating. If it does not fully dissociate, it's not a strong acid. Another thing is there are 6 to 7 strong acids that you will have to recognize to make things easier. So just as an aside, here are some strong strong acids for you to recognize. So HCl, HBr, HI, those are some strong acids. HNO3, H2SO4, HClO4, and one more that has been added to the list in the last 2 or 3 years, which is quite disturbing to me, is HClO3. These are all strong acids. HCl, HBr, HI, hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, perchloric acid, and chloric acid. These are all strong acids. That means they 100% fully dissociate. Okay? And then kind of connecting to a question about electronegativity and bond polarity, let me just focus on HCl, HBr, and HI. Cl, Br, and I all go down a group in the periodic table. Right? So if I had the periodic table, I have F, I have Cl, I have Br, and I have I. Okay? F is not part of this list. HF is not, that's a weak acid. It's not a strong acid, and I'm going to explain in a moment. As I go down, something is happening to these elements that the proton's attached to. I'm just going to draw a picture. I have HCl, HBr, HI. And this is because not only are my elements Cl, Br, and I getting larger as we go down a group, its electronegativity is decreasing. So size increases as you go down a periodic table. Now, we don't know this trend yet. I'm not going to make us recognize this until we get to the chapter on the periodic table. But something I will mention is as we go down a group, electronegativity decreases. And what electronegativity is that let's say I have an element, I'm going to talk about F. If I have element, it is the most electronegative element. What electronegativity really means, and my very scientific, very intellectual definition for electronegativity is how happy an element is with electrons. So if it wants electrons a lot, it's got a high electronegativity. I'm going to use En for electronegativity. If it does not want electrons, I'm going to say low electronegativity. Okay? And so, why am I talking about electrons? Well, this line that I drew here is a bond. And in that bond are electrons. Electrons are found in bonds. Okay? Now, if an element really wants electrons, it's gonna hold on to them tightly, right? So F is gonna hold on to electrons tightly. All right, so if it really wants electrons, it's gonna pull and hold on to whoever has electrons with it. It's gonna hold on to it tight. And F tends to form these small, tight bonds because it wants to bring all the electrons close to it. So HF, if I were to put that in this trend here, HF would be really tiny. And it's because this F is holding on to these electrons in the bond for dear life, right? And that makes it a weak acid because that H is stuck tightly in this bond to F. As you go down a group, notice how I was trying to draw the bond. This line is a bond. Notice how I was trying to draw the bond. As you go down a group, electronegativity decreases. Let's start with I here. I, 1, could care less about electrons, and 2, it's quite large. It's got so many electrons. So in doing that, that H is really, really far away. What is this H able to do if it's really, really, really far away? It's able to break off and dissociate. So by definition, if an acid could dissociate easily or fully, it's a stronger acid. And HCl, HBr, and HI, all of them have lower electronegativities than HF, or the F, actually. The F has the highest electronegativity than Cl, Br, and I. And because of that, all of these H's are able to dissociate off fully. So there was a question about electronegativity and bond polarity. If the bond polarity is quite different or completely opposite or large, that bond is tightly held and that proton cannot come off. If the bond polarity ends up lowering, or I have low polarity here or low electronegativity here and low electronegativity here, that H is not tightly held to the I, the Br, and the Cl, so it's able to dissociate. So because of that, if I had HI, if I put it in water, it's going to go straight to H plus and I minus, okay? But if I had HF, HF is going to weakly dissociate. And that's because this is a weak acid. That F is the most electronegative element, so it's really holding on to those electrons. So that's just like a quick aside about your strong acids and then quickly going about this electronegativity business and why electronegativity factors into strong acids. Basically, the lower my electronegativity, the stronger my acid. If I'm a proton and I'm attached to an element that has a low electronegativity, I'm going to probably fall off easily or dissociate easily, and I'm a stronger acid. Now going back to acid dissociation and then this buffer calculation, all right, I have this weak acid. This weak acid is going to dissociate in equilibrium. So HCN, and I'm going to get H plus CN minus, okay? So if I want to figure out how much H plus dissociated, right, and in my previous video I talked about how I could write H plus and Cn minus. If I want to figure out my concentration of H plus at equilibrium or even my pH, and this is a weak acid, I need to use an ice table because I'm already given a Ka of 4.9 times 10 to the minus 10th. The moment I have a chemical reaction or a chemical equation in equilibrium and I'm given a KEQ, and I want to solve for any concentration of anything, I probably want to use an ICE table. When in doubt, use that ICE table. Okay? So, if I'm constructing this lovely ICE table, I'm going to write down things that I know and things that I'm looking for. So, initially, I was given 0.1 molar of HCN. So, initially, I have all HCN, no H plus, no CN minus yet. This is before dissociation. Then during the change, mole-wise, for every 1 mole of HCN, I'm going to get 1 mole of H plus and 1 mole of CN minus. So minus X plus X plus X. This is like the BCA table. So you may want to watch an earlier video or go back to our notes on how we do BCA tables, but mole ratio says I'm going to use up 1 mole, and we're calling it X, 1X or 1 mole of HCN, and I'm going to make 1 mole of H plus and 1 mole of CN minus. I don't know how many moles yet because of the equilibrium constant, so I'm just going to label it as X, and then I write my equilibrium, minus X, X, and X. And then remember, the way we write KAs is concentration of products, or even KEQ of the acid is Ka. Concentration of products over concentration of reactants. For this chemical reaction, it should be concentration of H plus, concentration of CN minus, all over the concentration of HCN. And so my concentration of H plus and CN minus are my X here, and my concentration of HCN is 0.1 minus X. So this equals concentration of X, all over the concentration of 0.100 minus X. And this equals to my Ka, which is equal to 4.9 times 10 to the minus 10th. Now, I've talked about this in an earlier video and in the equilibrium chapter, and it came up in this acid dissociation chapter. If my Ka is very small, and so usually it's somewhere on the lines of 10 to the minus 4th to 10 to the minus 10th could be considered small. If my Ka is very small, this X in the denominator is negligible. This X is approximately 0 or very small. Right? So if this X in the denominator is very small, let's say I found out that X was 0.000001. If I do 0.1 minus 0.000001, I'm going to get about 0.1 left. That's what I mean by X is approximately 0. It's very small. It's negligible. So what I could do is I could cross out this X in the denominator and simplify this calculation. So it becomes X times X all over 0.11 equals 4.9 times 10 to the minus 10th. If I were to try and simplify these calculations, X times X, right, concentration of X times concentration of X is X squared over 0.1. So X squared over 0.1, now I'm doing this like backwards, X squared over 0.1 is equal to 4.9 times 10 to the minus 10th. If I want to solve for X, I want to isolate this X, so I have to multiply 0.1 by 4.9 times 10 to the minus 10th. This is algebra, so I got to multiply my denominator by both sides to get rid of it. So I'll get X squared is equal to 4.9 times 10 to the minus 10th times 0.100. All right, and I could do this all on a calculator. If I want to solve for X, I could do the square root of both sides. So just so you know, 4.9 times 10 raised to the minus 10th times 0.1. This is 4.9 times 10 to the minus 11th, by the way. And then if I want to do the square root of that, X equals, second square root of second answer, X equals 7.0 times 10 to the minus 6. Right? And that's a freaking small number. So this X being a small number makes sense for this. So if X is equal to 7.0 times 10 to the minus 6, what is X in my table here? Well, X is how many moles of my HCN, or my molar, of HCN that I use up. It's also, X is also equal to my concentration of H plus, and it's also equal to my concentration of CN minus. So X is equal to 7.0 times 10 to the minus 6 molar. It's equal to my concentration of H plus, which is 7.0 times 10 to the minus 6 molar. It's equal to my concentration of CN minus, which is equal to 7.0 times 10 to the minus 6 molar. If I want to figure out the concentration of HCN, I would have to do 0.1 minus X equals 0.1 molar minus, this was X, so 0.1 molar minus 7.0 times 10 to the minus 6 molar. So I could do 0.1 minus 7.0 times 10 raised to the minus 6, and I get 0.099993 molar. Yeah, negligible really. And so now that I have all of my, these are all my equilibrium concentrations, by the way, all equilibrium concentrations. And we did calculations like this in chapter 15 in equilibrium. So if I want to solve for X, I just plug X back into E here, and those are all my equilibrium concentrations. And then the last part of the question says, what is the pH? Well, pH is equal to the negative log of the concentration of H plus. So if I'm looking for my concentration of H plus, it's right here. So I'm going to do the negative log of 7.0 times 10 to the minus 6 molar. If I do this calculation correctly, negative log of 7.0 times 10 raised to the minus 6, I get 5.15. That would be my pH. So this is how we do a simple acid dissociation ice table. So this is a bit of a review for us. Be on the lookout for my next video where I try and actually do a buffer now.